I think you might have noticed this strange behavior regarding these agentic systems that are available today. Sometimes they give you the right answer, but when you look at how it got there, it makes absolutely no sense. Or worse, it solves a simple problem using 5 different tools when it could have done it in one step. So now the question is the AI actually good or is it just lucky? Because in traditional ML systems, the evaluation was simple. You had input, model, and output, and you just compared the answer with the ground truth. But with these modern AI systems, especially agents, things are very different. Now, the model is not just answering, it is thinking, planning, calling tools, retrieving information, and sometimes even correcting itself. So, if something goes wrong, what exactly do you measure? Do you check the final answer, the reasoning, the tools it used, or how efficient it was? And this is where most people get confused. And in this video, we are going to fix that. We will break down how to actually evaluate agentic AI systems in a way that makes sense, not just academically, but practically. And by the end of this, you'll have a clear mental model to judge any AI system, not just by what it says, but by how it behaves. We need to understand one critical shift here, because the way you used to evaluate machine learning no longer works. Let's start with the traditional step. In classic machine learning, like I said, everything is simple. You give an input and the model processes it and you get an output. That's it. Input, model, and output. And the evaluation is straightforward. You just compare the output with the correct answer. If it matches, the model is good. And if it doesn't, the model is wrong. Simple. But let's look at what happens with modern AI agents. The moment you give an input, the system doesn't just respond. It starts thinking. It breaks the problem into steps. It chooses to search for information, call an external tool, analyze the result, and then refine its answer. So instead of a straight line, you kind of have a loop, a process, a sequence of choices. And suddenly, input model output approach does not work. Here is the problem. If the final answer is correct, does that mean the system is good? Well, not necessarily, because it might have used the wrong reasoning, it might have taken unnecessary steps, or it might fail completely on a slightly different input. So the old way of evaluation, only looking at the final answer, is no longer enough. To truly evaluate an agent, you need to evaluate the entire journey, not just where it ended, but how it got there. Because you are no longer evaluating an answer, you are evaluating a process. So if we can't rely on the final answer, then what should we actually measure? So now we know that we can't just evaluate the final answer anymore. We need a better way to judge AI systems. And here's a simple mental model that solves this. Think of agent evaluation in 4 layers. Not 1, not 2, but 4. Each layer answers a different question. The first layer is output. Did the model give the correct answer? This is what most people focus on. And yes, it's important, but it's only the surface. The second layer, however, is reasoning. We try to answer that whether the model thought correctly or not. Because an AI can get the right answer with completely wrong logic, and that's quite dangerous. The third layer is behavior, where we answer whether the agent acted correctly. We ask questions like, did it choose the right tools? Did it avoid unnecessary steps? And did it interact with the system properly? Because agents don't just think, they take actions. And finally, the fourth layer is the system, where we answer the question, is the AI actually usable in the real world? Is it fast enough? Is it cost efficient? Is it reliable? Because even a correct AI is useless if it's too slow or too expensive. So instead of asking, did it give the right answer, you now ask 4 questions. Was it correct? Was it logical? Was it efficient in behavior? And was it practical to use? And this is how you evaluate modern AI systems. Most people generally stop at the first layer, or output. Experts evaluate all 4. And that's the difference between a demo and a production-ready AI system too. Remember, a good AI gives the right answer and a great AI gets there the right way. Now, let's break down each of these 4 layers and see how they are actually measured in practice. We'll start with the first layer, that is output evaluation. And this is the most familiar one, where we answer, did the model give the correct answer? At first glance, this feels easy. You just compare the model's output with the expected answer. If they match, it's correct. If they don't, it's wrong. But with modern AI, this becomes very tricky. Because unlike traditional models, LLM don't always give the same wording. 2 answers can mean the same exact thing and still look completely different. So if you rely on exact matching, you'll mark correct 2 answers as wrong. And here's the problem. So instead of strict matching, we move to semantic evaluation, where we answer, does the answer mean the same thing? Not is it identical, but is it correct in meaning? Now here's where it gets even more interesting. Sometimes there is no single correct answer. For example, summarization, explanation, open-ended questions don't have a single correct answer. So how do you evaluate those? You can't rely on fixed ground truth anymore. And that is where a powerful idea comes in, using another LLM as a judge. You give it the question, the model's answer, and ask it to score things like correctness, clarity, and completeness. Now suddenly, evaluation becomes flexible, also a bit subjective. So at the output layer, you're balancing between exact correctness, semantic similarity, and judgment-based evaluation. And each one has its own trade-offs, which mean even something as simple as is the answer correct is no longer that simple. Remember, correctness is no longer binary, it's contextual. But this layer also has its own limitations. An answer can be correct but poorly explained. An answer can be correct but not grounded in facts. And an answer can be correct but achieved through wrong reasoning. So if you only evaluate output, you can easily be misled. If you want to see a tutorial on the implementation of LLM as a judge, you can go to this link above and then check it out. However, we'll move to the next layer. Now, let's go one level deeper, reasoning evaluation. Because here's something most people don't realize. An AI can give you the correct answer, but for the completely wrong reason. And that should bother you. Imagine asking the model, what is 17 times 24? It gives you the correct answer. Sounds good, right? But when you look at its step, it made mistakes in the middle and somehow still landed on the right number. That's not intelligence, that's luck. And in simple cases, luck might work, but in complex cases like medical advice, financial reasoning, or coding, this becomes dangerous. Now, we ask a deeper question. Not just is the answer correct, but did the model think correctly? And this is what reasoning evaluation is about. We want to verify, are the steps logically consistent? Does each step follow from the previous one? And is there any hallucination in the reasoning? But here's the challenge. Reasoning is not always visible. Sometimes the model doesn't show its step. So we need techniques to bring reasoning out. And that's where methods like chain of thought prompting, step-by-step generation, and self-consistency comes in. They may force the model to reveal how it thinks. And once you can see the reasoning, you can evaluate it step by step. But in modern AI, getting the answer right is not enough. The path to the answer matters just as much. So to summarize, to evaluate reasoning, we don't just look at the final step. We inspect the entire chain, step by step. We check whether the steps are valid. We check whether there are any logical jumps or not. And we check whether the model is making any assumptions or not. And in advanced system, we even use another AI to verify each step. Remember, a correct answer with wrong reasoning is a hidden failure. So now we've evaluated the answer and the reasoning, but agents don't just think, they act. So we need to go to the behavior evaluation of it, and we'll discuss this in the next part. So like I said, the third layer is the behavior evaluation. And this is where things change completely. Because until now, we were only looking at what the model says. But like I said, agents don't just talk, they act. They use tools, they make choices, they interact with the system. So now the question becomes, did the agent behave correctly or not? We'll take a simple example. You ask an agent, find the weather in Kathmandu. Now, a good agent should call a weather API, get the result, and return a simple answer. But what does a bad agent do? It might search the web unnecessarily, call multiple tools for the same task, repeat steps, or even hallucinate the answer instead of using tools. Now, here's the key idea. Even if both agents gave you the correct answer, their behavior can be completely different. And that matters because behavior determines cost, speed, reliability, and scalability. So in behavior evaluation, we don't just ask was the answer correct, we ask was the process efficient and correct or not. We measure things like did it choose the right tool, did it avoid unnecessary actions, did it follow the optimal path, and did it repeat or loop unnecessarily. Because in real systems, an agent that is slightly inefficient can become extremely expensive and scale. So even if the output is perfect, bad behaviors can still make the system unusable, and that's why this layer is critical. In simple terms, output tells us what it said, reasoning tells us how it thought, and behavior tells us how it acted. Remember, correct output does not guarantee correct behavior. In production systems, behavior is often more important than correctness because every extra tool costs money, every delay reduces user experience, and every loop increases failure risk. So an agent that behaves poorly is not scalable even if it is accurate. So now we've evaluated the output, the reasoning, and the behavior, but there is still one final layer. And the final layer is system evaluation. And this is the layer most people completely ignore because up until now, we've been focusing on correctness, reasoning, behavior. But there's one more question that decides everything in the real world. Is this system actually usable at scale? Let's say your agent is correct, logically sound, and behaves efficiently. Sounds perfect, right? But now imagine this. It takes 30 seconds to respond. It costs $2 per request, and it fails 1 out of every 10 times. Would you deploy it? Probably not, because in real systems, performance is not just about intelligence, it's about practicality. So in system evaluation, we measure things like latency, answering how fast does the system respond, cost, answering how many tokens or API calls does it consume, reliability, answering how often does it fail or break, and scalability, answering can it handle 10 users or 10 million users. And this is where many AI projects fail, not because the model is wrong, but because the system is not usable. So even if an AI system or AI agent performs well in isolation, it still needs to pass the system test, answering is it fast enough, is it cheap enough, and is it stable enough? Because at the end of the day, you're not just building a model, you are building a product. Remember, a great model is useless if the system around it is not scalable. And most AI failures in industry are not model failures. They are system failures, meaning they're too slow, or they're too expensive, or they're too unstable. That's why system evaluation is the final gate before deployment. So when you evaluate modern AI systems, you're not just asking one question anymore. You're asking four, because intelligence alone is not enough. The real question is, can this AI actually work in the real world? So in this video, we broke down something most people completely misunderstand: how to actually evaluate agentic AI systems. We started with the basic idea that you can't just look at the final answer anymore, because modern AI systems don't just respond. They think, they plan, they use tools, and they act. So instead of one simple metric, we now need 4 layers of evaluation. First, we looked at output evaluation. Is this answer correct? Then reasoning evaluation. Did the model actually think correctly? Then behavior evaluation. Did the agent act efficiently and use tools properly? And finally, system evaluation. Is the entire setup fast, cheap, and reliable enough to use in the real world? And when you combine all 4, you start to see something important. AI evaluation is no longer about checking answers. It's about understanding systems. Because a model that is correct but slow or expensive or logically flawed is not really useful in production. So the next time you look at an AI demo, don't just ask, is it working? Also try to ask, is it correct, logical, efficient, and scalable? Because that is how real AI systems are judged. So if you found this helpful, do write down in the comment below, and I'll try to continue this series by breaking down how these agents are actually built, step by step, from simple to production grade systems. We're building something really next level. That is a multi-agent AI system that doesn't just answer questions. It thinks, plans, executes, and reviews its own response all by itself. Now, before we jump into the code, let me show you the big picture of what we're going to build. So imagine a workflow like this. First, a planner agent reads your question and comes up with a short actionable plan, like a strategist plotting the best way to tackle a problem. Next, a worker agent takes that plan and generates a detailed answer. The doer who writes, codes, or explains based on the plan. Then we'll have a reviewer agent in to critically check the response. That will look for clarity, concrete examples, trade-off, and actionable recommendations. If something is missing, reviewer agent will send it back to the worker for improvement. And finally, we'll have the workflow loop intelligently. That is, the worker can revise its output based on the reviewer feedback until the response is high quality and approved. And by the end, what we'll have is not just a single answer AI. It's like a team of AI experts collaborating to generate responses that are actionable, accurate, and ready for industrial applications. We're going to implement this using Python, LangGraph, and Groq's Groq LLM. Step by step, we'll code each agent, connect them into a dynamic workflows, and even visualize the flow so you can see exactly how the agent interact. And by the end of this video, you'll have a fully working multi-agent AI system, and more importantly, you'll understand how to design workflows that can learn and improve themselves, the exact kind of architecture used in cutting-edge AI product today. So, let's dive right in. I've already created a virtual environment for this project, so everything stays isolated and clean. That's a really important habit, especially when you're building AI applications, because different projects often depend on various library versions, and a virtual environment will help us to avoid version conflicts. Here I've also created a .env file where I have stored my Groq API key. Now this is the key that will allow our application to securely access the large language model, and this is the right way to do it in real projects. So instead of hard coding your API key directly inside your Python script, which you may share at some time in maybe some repository, and it's quite risky and unprofessional, so we keep sensitive credentials inside environment variables. Next, I've also prepared a requirements.txt file with the libraries we are going to need for this project, and these are the libraries we'll install here. So we'll understand why we need each of these, because this is not just about installing random packages. So each one has a very specific role in the system we're building. First, we have LangGraph. So this is the core library that will allow us to build our multi-agent workflow as a graph. So in our case, we'll define various nodes like planner agent, worker agent, and reviewer agent, and then we'll connect them with edges so the execution can move from one agent to the other. So this is what gives structure to our agentic AI system. Next, we have LangChain. Now you can think of this as the general application framework that helps us work with language models more effectively. So it'll give us abstraction and utilities for building LLM powered applications. Even though our main orchestration is happening through LangGraph, so LangChain will provide us a broader ecosystem and compatibility that will make these integrations very easier. Next, we have LangChain Groq. So this is the specific integration package that will allow us to connect our LangChain based application with Groq's natural language models. So since we'll be using Groq to power the intelligence of our agents, so this package is what lets us initialize and call the model directly from our code. Now also we have the python.env. So this libraries will allow us to load environment variable from .env file that we've created into our Python application. So when we store the Groq API key in .env file, python.env helps us bring that key into runtime environment securely and confidently. So altogether, these four libraries are going to give us everything we need. So they'll give us a graph-based workflow engine, LLM application support, Groq model integration, and secure environment for variable handling. Now that the setup is ready, we can go ahead and install these dependencies. So to do that, I'm going to do pip install -r requirements.txt inside my virtual environment, which is already activated here. So we'll allow for this installation to be complete. Now that the virtual environment installation or the library installation inside virtual environment is complete, we have another file called app.py in which we are going to write our main logic here. So we'll start with import first. I'll type in the code and then I'll explain what each of these libraries are going to do. Load.env chain, LangGraph import state graph and langchain underscore Groq import chat Groq, and we'll have this load.env function. So at first we've imported the OS module. So this is a built-in Python module that allows us to interact with operating system. Things like creating folders, handling file paths, and managing files. We're going to use this later in the code to create a logging directory and store output from our agent. Next, we have the logging module. So this is important for real-world AI systems. So when you're using production grade applications, you don't want to rely only on print statements, right? So logging allows you to track what each agent is doing, record system events, and maybe even debug issues if something goes wrong. Then here we import load.env. Like I said, we've created a .env file earlier, right? So this particular function will allow our Python application to load those environment variables such as our Groq API key directly into our runtime environment. So next, we import the core component that will power our multi-agent workflow, which is state graph from LangGraph. And LangGraph allows us to build workflows where various agents act as node in a graph. So instead of writing a rigid linear script, we can actually interpret a dynamic flow where execution moves from one agent to another depending on the conditions. So for example, in our system, the planner agent will run first, then the worker agent, then the reviewer agent. And if the reviewer thinks that the response needs improvement, the workflow can loop back to the worker again. So this kind of intelligent routing is exactly why LangGraph is so powerful for agentic AI. So here we've also imported end, which simply tells the workflow where executions should terminate once our agents are done. And then next we import the LLM that will power the intelligence of our agent. So this is the Groq integration for LangChain. So it will easily allow us to connect our application to Groq's large language models. And all of our agents, the planner, worker, and reviewer, are going to use the same model to reason, generate response, and evaluate outputs. So now that our output are ready, I have inserted a load.env function here. So like I said, this line will query our .env file, and then it will load all the variables into our application, which means our Groq API key now becomes available automatically without us having to hardcode it anywhere in this particular script app.py here. And now we are going to initialize the LLM that our agent is going to use. So for that, I can do LLM chat Groq, and then the model name I'm going to define as Llama 3.3. This is a 70 billion model, and let's say versatile. So this will be the model here, and here we have created an instance of the chat Groq model. So we're using the Llama 3.3 model, which is a powerful general purpose reasoning model capable of handling, planning, writing, reviewing, and analytical tasks. So at this point, our system is ready with three important things here. First, we have our libraries required for doing the workflow. Second, we have secure environment variable loading. And third, we have a powerful language model that will act as a brain behind all of our agents. So now that we've completed all of these three steps, the next thing we're going to implement is something that many tutorials tend to ignore, but every real-world AI systems absolutely need, which is proper logging. So when you're building multi-agent systems, several agents are working together, right? They're passing information back and forth, and sometimes they're looping multiple times before providing a final answer. So if something goes wrong, or if you simply want to understand how your system has arrived at a result, logs become incredibly valuable. So instead of relying on print statement, what we'll do here is we'll create a structured logging system that records everything happening inside our workflow. So the first thing we are going to do is we are going to define a folder where all of our logs will be stored. So for that, I'm going to define log_dir equals to logs. So logs will be the folder where we'll save execution logs and output generated by our agents. Now next, we'll ensure that this directory actually exists. And for that, we're going to use the OS library. So os.make directory, I'll say log dir, and then if it exists, then I'll do if exist okay equals to true. So what this line does is this line tells Python to create the folder if it doesn't already exist. So the exist okay equal to true flag ensures that if the folder is already there, Python will not throw an error. So this is a small detail, but it's a very common practice in production grade applications. So now we'll configure the logging system itself. So logging equals, logging dot basic config. Inside this, I'm going to provide a file name. So file name equals to os.path join path join log directory, and then let's call it execution.log. So execution.log is going to be my file name. Now the level for this is logging.info. I'll also provide the format. So the format will be defined in string, but we'll have ESC time s minus percentage level name s minus percentage message, and we'll also have a file mode. So file mode I'll write as W. Okay, so first we have specified a log file location here. So we are storing the log file inside the logs folder and naming it execution.log. So this file is going to record everything that happens when the system runs. Next, we have set the logging level to info. So logging level actually controls how much details gets recorded. So info is a good balance because it can capture important events without overwhelming us with unnecessary debugging information. Then we define the format of each log entry. So each line in the log will contain a timestamp that will be provided by this, the log level that will be provided by this, and then the message itself. So this makes it very easy to trace what happened and when it happened. And finally, we've set the file mode to W, which means every time we run the program, the log file will start fresh instead of appending to the old logs. So now we create the actual logger object that we'll use throughout the application. So for that, I'm going to do logger equals to logging dot get logger, and I'll put in underscore name here. So the logger here will allow each agent in our system to record its activity. So for example, when a planner agent starts, it will log that event. And then when the worker generates a response, that will also be logged. And when the reviewer approves or requests revision, we'll capture that as well. Now, there's one more utility function we'll need to define that will help us store outputs generated by our agent. And for that, I will define a function called writeTextFile. Here I'll pass in the file name as a parameter and then a content as a parameter, and both of these will be in string. So file path equals to os.path.join log directory file name, and here we'll have with open file path. We'll use the same file mode W, which means we'll start fresh. Encoding equals to UTF-8 as F, and then I'll do F.write content. Okay, so this function will simply write text inside our folder inside our logs directory. So we will use this to store output from different agents here. So for example, the planner's plan, the worker's draft response, and the reviewer's feedback will all be saved as a separate file, and that is going to make it very easy to inspect the intermediate steps of our multi-agent system. So now that we've done something very important, we've added observability into our AI system. That means we can now monitor what each agent is doing, inspect intermediate outputs, and debug issues more easily. So this is exactly how production AI systems are built. Not just generating output, but also recording everything that happens during execution. So now comes the most exciting part. So now we're going to start implementing the actual agents. So beginning with the planner agent, which will read the user query and generate a strategic plan for the rest of the system. So in many traditional AI applications, we ask a model a question and then immediately generate an answer. But in agentic AI systems, we often separate thinking from doing. So the planner agent that we are thinking about here will be responsible for understanding the user's query and creating a strategy for how the system should answer it. So you can think of it like a project manager who first identifies the approach before the team starts working. So we'll start by defining the planner agent function. So we'll keep it inside a function declaration, planner agent state. So every agent in our LangGraph flows receive a shared object called the state here. So the state is essentially a dictionary that holds all the information flowing between agents. So things like user's query, the generated plan, the draft response, and the reviewer feedback. So agent are going to read from the state and update it and then pass it along to the next agent in the workflow. Now the first thing the planner does is log that it has already started running. So inside this, let me type logger.info. Let's say planner agent started. So if you remember that we built a logging system earlier here, so the line will record in the log file that the planner has begun its execution. So next we'll also log the user query that the system has received. So for that I'm going to do logger.info. I'll pass in the user query and then I will actually obtain it from the state. Again, we have not defined our state variables yet, but we'll do that later on when we reach to that particular part. So what this will do is this will help us track exactly what input triggered the workflow or what query triggered the planner workflow. Now comes the important step or the key step where we'll construct the prompt for the language model. And for that, I'm going to type everything by myself here. So the prompt is going to be, I'll create a multi-line string for this prompt so that I can type everything here. So I'll say you are a planning agent in a multi-agent AI system, and your job is to read the user's query and create a short plan for how the worker agent should answer. So I'm going to pass in the user query as, again, I'm going to retrieve this from the state here. So state user underscore query, and I'll say return only a short actionable plan. So here through the prompt, we are instructing the model to behave specifically as a planning agent. So instead of answering the question directly, so the model's job now is to analyze the query and produce a short actionable plan that the worker agent can follow. So the separation of responsibilities is extremely powerful here. It allows us to break complex reasoning into smaller steps, planning first and execution later on. Now next we're going to send this prompt to our language model, and for that I'm going to do response equals to LLM.invoke and then write prompt. So the line will call the Groq model and ask it to generate a response based on the prompt we constructed. So different LLMs libraries sometimes return output in slightly different format. So here we safely extract the text response. So for that I'm going to do plan equals to response.content if has attribute, let's say response content, else str response. So basically our plan will be inside response.content. I just wanted to put as a part of exception handling here. So now that we have our LLM response, we'll store that plan inside our workflow state. So to do that, I'm going to do state plan equals to plan. So this particular statement is particularly useful and important because the next agent, which is our worker agent, will read this plan from the state and then use it to generate the final response. So next what we're going to do is we will save the planner's output to a file. So for that I'm going to call the write text file function that we created earlier. I'll call this planner output.txt and then put the plan content inside this. So this will allow us to inspect the plan generated by the planner agent later on. So, and then that will be very helpful for debugging and analyzing how our system is thinking. And finally, I'll go to the planner's output and log it. So logger.info, let's say planner output, then put it inside plan. So this particular statement is going to record the generated plan inside the log file for traceability. And finally, I'm going to return state here. Okay, so the planner agent is almost complete. So what this returning state does is this particular part is how information flows through our workflow. So the planner updates the state and then the LangGraph passes that updated state to the next agent. So what did we do here? So the planner agent will read our user query, create a strategy for solving it, save the plan inside a shared workflow state, and then pass it to the next agent. So this simple separation between planning and execution is one of the key pattern in modern agentic AI systems. So next we'll move on to the worker agent, which is the agent that actually takes the plan and then produces a detailed response for us. So if the planner is the strategist of our system, the worker is the one who actually gets the job done. So the worker agent will take the plan generated by the planner, reads the user query, and produce a detailed response. But there's something interesting here. The worker can also improve its response based on the reviewer feedback, which means our system can refine answers iteratively. So we'll start by defining the worker agent function. Def worker underscore agent state. So just like before, the agent receives a shared state object, and then this contains everything the previous agent has produced, like the user query, the plan, and possibly the feedback from the reviewer too. So the first thing we do here is track how many times the worker has been called. So for that, I'm going to do state worker underscore calls plus equals to 1. So if the reviewer thinks the response needs improvement, the system will send the task back to the worker, right? So by tracking the number of calls, we can monitor how many revisions has been already made. So next, we are going to retrieve any feedback that is provided by the reviewer. At first or when the first time the worker agent is called, obviously the review reason will be absent. But in case the worker agent has been repeatedly called, then we will have a feedback. So to track that, I'll have feedback equal to state.get review underscore reason, and then I'll put a empty string for default case here if we don't have review reason at all. Now we will log the worker execution. So for that, I'm going to do logger.info worker call. Then I'll provide the number, how many times the worker has been called. And for that, I'm going to trigger state worker calls. Okay, so this will track how many times the worker agent has run during our workflow execution. So next, we again come to the important part where we write instructions for our worker agent, which is the prompt part. So for prompt, I'm going to write it manually here. So prompt equals to, again, use a multi-string format to write my prompt. And here I'll write you are a worker agent. So I'll pass in the user query. So the user query come from the variable user underscore query. Not from here, sorry. I'll pass it to state here. So user underscore query from state. And then I'll have plan from state. Again, keep it inside braces to treat it as a variable, and then access state plan. Then previous reviewer feedback, then that will come from feedback because I've already extracted it from here. And finally, I'm going to write some instructions. So write the best possible improved response if reviewer feedback exists, explicitly fix those issues. Okay, so a prompt part is complete here. So the prompt gives the worker 3 pieces of information here. So the first, it provides an original user query. Second, it provides a plan created by the planner agent. And third, It provides the feedback from the reviewer if the response needs improvement. So this is what allows the system to behave like a collaborative AI team. The worker doesn't just generate an answer, it follows a strategy and incorporates feedback. Next, we will send this prompt to the LLM. So for that, I'm going to do response equals to LLM dot book prompt, and like we did earlier, so we will safely extract the response text. So for that, I'm going to do draft underscore response equals to response dot content if in fact the response has an attribute content, else I will keep draft response as str response. Next, what we're going to do is we're going to store the generated draft inside the workflow state. So state write draft response equals to draft response that we've extracted earlier. So this particular draft will be passed to our reviewer agent, which will evaluate whether the response is good enough or needs improvement. And finally, we will save the worker's output to a file, and for that I'm going to call this write text file function. Here I'll pass in the worker underscore output underscore state worker calls, and then pass in .txt here, and then inside this file I'm going to save draft response. So if you notice this part here, so each worker output is saved with a different file name based on the call number. So that means if the response gets revised multiple times, then we'll be able to inspect each version separately. And now this becomes extremely useful when analyzing how the system improves over time. Next, we log the worker output. So logger dot info, I'll write worker output, the same thing again. Let me just copy it from here, because we are going to use the draft response itself. So I'll just use this worker output. I don't need this txt part, and inside this I will have draft response. And finally, we are going to return the state. So this will pass the generated draft response forward to the next agent in our workflow. So what we have built just now is an agent that can generate response based on a strategy and feedback. In traditional AI system, the model generates a single response and that's it. But in case of agentic AI systems like this one, responses can be iteratively improved through collaboration between agents. And now we are ready for the next component here. So that will be our reviewer agent, which will critically evaluate the worker's response and decide whether to approve it or send it back for revision. So if the planner is the strategist and the worker is the executor, then the reviewer will act as a quality control expert. Its job is simple but extremely important here. So it will evaluate the worker's response and then choose whether the answer is good enough or whether it needs revision. So this is a key idea in modern AI agentic systems. Instead of trusting the first answer provided by the model, we add a self-critic stage where another agent checks the work. So let's start by defining the reviewer agent function. Def reviewer underscore agent. We'll pass in the state. Again, we will have a shared state object here that contains the user query, the plan, and the draft response that is generated by the worker. And inside this, first of all, we'll keep track of how many times the reviewer has run. So I'll use state again, reviewer underscore calls plus equals to 1. So this is going to help us monitor the number of review cycles that has happened during a particular workflow. And now we directly move on to constructing a prompt that will guide the reviewer's evaluation. So let me write the prompt here. Again, I'll use a multi-line string format. So here, let me write you are a strict reviewer agent. I'll pass the user query, and that will be obtained from state user underscore query. Then I'll pass a draft response, and that will be obtained from state draft underscore response. And for the instruction, what I'm going to say is check for, first of all, concrete examples, implementation details, trade-offs, clarity, and actionable recommendations. And also, if anything is missing, then revise. And finally, return exactly in this format. Decision is to approve, revise, and then a reason which will contain a brief reason here. So we're instructing the model to behave like a strict reviewer and not just a passive evaluator. So it will check for several important qualities as mentioned here. And these are exactly the kind of thing that separates a high quality answer from a vague one. And then we also force a model to respond into a structured format. So returning a choice and a reason. So this makes it easier for our system to parse the output and then make routing choices. Now we'll send this prompt to the language model using response equals to LLM dot invoke, and I'll use prompt. Next, we extract the raw output from the model. So I can do raw underscore output equals to response dot content dot strip if response in fact contains content, or else I'm just going to use the string form of response. Now what we do is we now interpret the reviewer's choice. So for that, I'll do decision equals to approve if decision approve in raw output dot lower, else revise. So if the model says approve, the workflow will move forward and finish. Otherwise, the responses will be sent back to the worker agent for revision again. And next, we extract the reason provided by the reviewer. So for that, I will do reason underscore line equals to. Next, now this will go in loop. So line for line in raw output dot strip lines if line dot lower dot starts with and if it's not present, I'll just put a empty string here. And finally, I'll do reason equal to reason underscore line, replace a reason with empty string dot script if reason underscore line else no reason provided. Okay, so this will allow us to capture the specific feedback explaining why the response need improvement, and this feedback will be sent back to the worker agent so it can fix those issues. So now we'll store the reviewer's choice and reasoning inside the workflow state. So state review decision equals to decision, and state review reason equals to reason. So this information will be used by the routing logic again to identify what happens next. And just with the other agents, we'll also save the reviewer output to a file. So since this is a long code, I'm not going to type everything. So let me just paste this here. And this is going to let us inspect exactly how the reviewer evaluated the response. Next, we are going to log our reviewer result, which will create a clear trace of the decision-making process in the logs. And then finally, we are going to return state. So this allows the workflow to continue based on the reviewer's choice. So here what we've built is an agent capable of AI self-critic. So instead of blindly trusting the first answer generated by the model, our system now has a mechanism for evaluating and improving responses. So this pattern, generate, review, and revise, is widely used in advanced AI systems to significantly improve the output quality of our agent or of our LLM. And now comes the really interesting part. So now we'll implement the routing logic that identifies whether the workflow should end or send the response back to the worker for improvement. And this is what turns our system into a true feedback loop where agents collaborate to produce better results. So here we are going to implement a small function called the review router, and this function will fix the next step in our workflow. So let's start by defining the router, and for that I'll do def review underscore router, and again we'll have a common shared state object. So the first condition that we're going to insert here checks whether the reviewer approved the response or not. So for that I'll do if state.get review decision equals to approve, or state.get, let's add one more condition, review underscore count, which by default is 0, is greater than or equals to 2. So if the reviewer says that the response is good enough, then our job is done. But we've also added another condition here. We're limiting the number of revisions. So if the system has already revised the answer 2 times, we are going to stop the loop even if the reviewer still wants changes. So again, why this part? Because this is a very practical safeguard in real world applications, because without this, the workflow could potentially loop forever looking for that perfect answer. So if either of these 2 conditions is met, then we'll terminate the workflow, which means we're going to return score END. So in LangGraph, returning end signals that the workflow execution now should stop. But what happens if the reviewer says that the response still needs improvement? So in that case, first we're going to increase the review counter. So state revision underscore count equals to state get revision underscore count comma 0 plus 1. So this is going to keep track of how many improvement cycles the system has gone through. And now we route the workflow back to our worker agent, which means I'm going to do return worker underscore agent. So this will create a feedback loop, and then the worker will receive the receiver's feedback, improve the response, and send it back for another review. So this small function gives our system iterative intelligence here. So instead of generating a single answer and stopping, our AI system now follows a cycle. It generates a response, reviews the response, and improves the response if required. So the pattern generate, critique, and refine is widely used in advanced AI architectures because it significantly improves the output quality. Now that our routing logic is ready, the next step is to connect all the agents together into a workflow using LangGraph. And this is where we'll define the structure of our multi-agent system, essentially building the graph that controls how the agents interact. So what LangGraph does is it allows us to represent the workflow as a graph, like I said, where agents are nodes and the execution flow between them is represented as edges. So we'll start by creating the workflow agent. So let's write workflow equals to state graph, and then I'll pass in a dictionary. So here we're initializing a LangGraph state graph. So this graph is going to manage the execution of our agent and pass around the shared state dictionary that contains the information like the user query, the generated plan, the draft response, and the reviewer feedback too. You can think of this state as the memory of the workflow, allowing agents to collaborate by reading and updating the shared information. So next in this, we add our agents to the graph. So I can do workflow dot add node. So each of these agents is going to be represented as a node. So first of all, I'll have a planner agent, and for that I have a function called planner agent. Next, I have workflow dot add node. Again, I have a worker agent which has its own function, worker agent we've defined earlier. And finally, I'll add one more node, add node, where we'll have a reviewer agent. We also have a function for this already above. So the planner agent will create a strategy for answering the query. The worker agent will generate the response based on plan. And then the reviewer agent will evaluate the response and choose whether it needs improvement or not. So by registering them as node, LangChain now knows that there are 3 executable components in our workflow. Now next we define our entry point, which means we define where the workflow should start. So now for that entry point, I am going to set its entry point using the set entry point function, and then I'm going to name planner agent. So the agent workflow should start from planner agent, which means whenever the system receives a query, executions will actually begin with the code written in the planner agent function. So that makes sense because the system should always plan first before executing. Now next we define the normal flow of our execution, and for that I'm going to add edges now. So first workflow dot add edge. So from the planner agent, we will move to worker underscore agent. That means once the planner agent finishes creating a plan, the workflow moves to the worker agent. Next, workflow dot add edge, worker agent, reviewer agent. So after the worker generates our draft response, the system sends that response to the reviewer agent for evaluation. And after this, we implement the intelligent routing logic. So for that, I'm going to do workflow dot add conditional edge. And then the starting point is actually the reviewer agent here. And the part where we're going to go is not to any agent, but to this review router function. So review underscore router, and then we're going to check something here. What we're going to check here is we are going to check if in the router we passed it to end of the workflow or to the worker agent. So if worker agent is present, then we go to worker agent, and if is the end, then we end the workflow. Worker agent, and then end. So here the reviewer agents first evaluates the response. LangGraph then calls our review router function. Send, and then the function actually chooses whether to send the task back to worker agent or to end the workflow completely. And now this creates a feedback loop into our system, and the worker can improve the response multiple times until the reviewer finally approves it. Once all the nodes and edges are defined, now we're going to compile the workflow. So for that, I'm going to app flow.compile. So from this point onwards, we can simply invoke the workflow with an initial state, and LangGraph will handle the entire orchestration of agents. So we've just built a structured multi-agent pipeline that works in the following way. So the first, planner reads a user query and then creates a plan. Worker then generates a response based on that plan. Then the reviewer evaluates the response, and if required, the response is improved through revision cycles, sending it back to the worker agent, or by ending the workflow if the output is simply acceptable. Now we will generate a visual diagram of our workflow graph, so we can clearly see how these agents are connected. Since the code is quite error prone, so I'm just going to paste this, and then I'll try to explain what I'm doing here. So we will start by wrapping the visualization inside a try except block. We do this because visualization depends on certain optional dependencies. So if something goes wrong, we don't want our main application to crash. Now we generate the graph image here. So the LangGraph internally converts our workflow graph into a mermaid diagram, which is a popular format used for visualizing flowchart and system architectures. Then it automatically renders that diagram into a PNG image. So essentially, our code is turning the agent workflow into a visual architecture diagram. And next, we save the generated image into a file. And after saving the diagram, we log a message confirming that the graph was generated successfully. And finally, if something goes wrong inside our try block, or if something goes wrong during visualization, we catch the error, and in this way the application continues running even if the visualization step fail. So we built our agents, connected them to a workflow, added logging, and even generated a visual architecture diagram. So now it's time to actually run our multi-agent system and see it work. So for that, first we are going to ask the user to enter a query. So let me write user query equals to, I'll use the input function for this, enter your query. Now, user will interact with the system from the terminal and provide a query for the system. So next, we're going to log this user query. So user input, user underscore query. Then we will define the initial state of our workflow. And again, just so that I don't make any mistakes, I'm just going to copy this because this is quite error prone. So if you remember, we talked about the shared state object that flows between agents, right? So each function had this state parameter here. So this particular initial state part is exactly that state. So it acts as the shared memory of the workflow, allowing agents to store and access information during execution. So the shared state will enable the agents to collaborate effectively. So here we have user query, plan, draft response, review reason, review decision, worker call, reviewer call, and revision count, which we have all used earlier here. Now next, we will execute the workflow, and for that I'm going to do a result equals to app.invoke, and then I'll pass in the initial state. So what is our app? Our app is our workflow. So this single line will trigger the entire multi-agent system. The multi-agent system. So LangGraph is going to take the initial state and start executing the workflow from the entry point that we fixed earlier, which is the planner agent. From there, the workflow moves through the graph automatically, and all of that orchestration happens automatically here. And once the workflow finishes, we're going to extract the final response. So for that, I'm going to do final response or final output equal to result get graph response. And let me keep a default empty string here. So this will retrieve the latest graph response from the workflow state, which should be the approved final answer here. So again, we are going to save it to a file just so we can re-evaluate it or maybe go through it manually later on after we get the output, and then we will print our final response, which we will be seeing in the terminal window here. And of course, we want to log the final result as well. So we'll log the final result, ensuring the entire lifecycle of the workflow is recorded in the logs. So what we built here is not just a simple AI script. We implemented a collaborative multi-agent system where different agents specialize in different tasks. And through conditional routing, the system can iterate and refine its response automatically. Now, this kind of architecture is being increasingly important in modern AI systems, especially when building reliable and high-quality AI assistants. And the best part is that you know exactly how to build one using Python, LangGraph, and Groq. So now, before we end the video, we're going to see the output and then evaluate the output, evaluate the kind of the output that this particular agent will generate. So to evaluate the model or to check the response, I'm going to run this app.py. So if we don't have any error, then we should run it, but we do have some errors. I think I know what the error is. So let's go to line 104, and I think I missed a comma here. 104. Reason. I think this should be replaced with a comma. So save it and run it again. by passing the API key to the Groq API key variable. So let me check if we have loaded our parameter or our variable or not. Okay, we've done it. I've checked my .env file, and then my file does contain the API key. So let me run this again. Okay, so the system is asking me for a query, and then I'm going to paste the following query here. So the question is, explain the pros and cons of using microservices architecture versus monolithic architecture for a large-scale e-commerce platform, and provide a step-by-step plan for migration from monolith to microservices. So this is my query. So let me run this. Okay, so there is an error again. Line 148. Let's see line 148. Okay, so this should have been info. This again. Same query. Okay, there seem to be too many mistakes, typing mistakes here. Where is this? Line 37. Line 37. It should be user query. Clear this, run it again, paste the query. Okay, so we do have some more error. So this is in line 103. So let me check 103. This should be split lines, sorry. Split lines. Clear this again. So we're debugging it one error at a time. Okay, seems like it's running, or our agent seems to have started their work. Let me evaluate the logs here. So we can see that there are frequent revisions that has been going on. I think we're going to run out of tokens if these revisions do continue for us. So we'll see if we'll get a final answer or not. So the reviewer output has run up to 7 times, 6 times, and 7 times, which means even if we don't get an answer, I think I messed up with the stopping part here. Or review count. Okay, I think I forgot to update the review count part, which is why the worker output or the reviewer output has been going on and on and on for multiple epochs. So if we open out any of these, okay, I'll first start with the planner output. So here here the model has simply laid out a plan. So it says, to address the user's query, I plan for the worker agent to research and list the pros and cons of microservice and monolith architectures, identify key difference, and then it outlines a step-by-step plan. So now the worker output creates something based on the plan created by our planner agent, and then this particular worker output is then reviewed here. So the review choice, so the reviewer has made a point to revise it, because the reason is that the response lack concrete example, implementation detail, and so on. So based on this, the worker output has revised its output here. And then if we go to number 2, again, the response is comprehensive, but it lacks concrete examples. So the reviewer has sent it to worker agent again. So it goes to worker output 3. It generates the response again. Now the reviewer output has chose to approve, but okay, I think I messed up with the code. This should have stopped from the reviewer output 3, because in 4, 5, 6, okay, this should have been stopped earlier. So anyway, we do have something something here. Our planner agent, worker agent, and then the reviewer agent is working continuously. But let's check where did we mess up. So the review router should have ended. Let's see the review router part. If the review decision is approved, okay, what was the review decision? Let's check. Did we put the review decision in decision here? Okay, we did. And then if the review decision is approved, then it should have ended. What was the review decision? Sorry, the review output 3. It was approved, so it should have ended. Okay, but anyways, we have successfully created something or a multi-agent platform that works coordinately, and then we've all binded them together using LangGraph. We start by importing the code libraries required for building our agent evaluation systems. First, we bring in standard utilities like OS and logging, which helps us manage files and track system execution. Next, we load environment variables using .env, which allows us to securely manage API keys and configurations outside our code. We then import LangGraph, which is the framework we use to build our multi-agent workflows. It allows us to define agents as nodes and connect them into structured execution graph. And finally, we import Groq from LangChain, which gives us access to a large language model, in this case Llama 3.3, that powers all the reasoning and generation inside our system. We first load environment variables using load.env, which helps us securely access our configuration from .env file. Then we initialize our language model using Groq with a Llama 3.3 70 billion model, which will act as the core reasoning engine for all of our agents. Next, we set up logging for the system. We create a dedicated logs directory to store all the execution traces and outputs. Then we configure Python's logging system to record events like timestamps, log level, and messages into an execution log file. So this will help us debug and analyze how each agent behaves during execution. And finally, we define a utility function that allows us to save intermediate outputs into separate text files for easier inspection and evaluation. Now we define the planner agent, which is the first reasoning component in our multi-agent systems. So the role of this agent is not to solve the problem directly, but to understand the user's intent and convert it into a structured plan that guides the next stage of execution. At the beginning, we log that the planner agent has started. So this is useful for tracing execution flow when multiple agents are interacting in sequence. Next, we construct a prompt for the language model. In this prompt, we explicitly instruct the model to act as a planning agent and generate a short actionable plan based on the user's query. We pass the user query from the current system state into the prompt so that the planner has full context of the text. The response from the language model is then extracted. Since LLM responses can sometimes come in different format, we safely check whether the response has a .content attribute or not, and fall back to string conversion if needed. And once we obtain the plan, we store it inside the shared state object. This allows all downstream agents, especially the worker agent, to use this structured plan as guidance. We also process the plan into a separate file called planneroutput.txt. This is important for evaluation because it allows us to inspect what the model intended before execution. And finally, we return the updated state so that the next agent in the pipeline can continue processing with this structured plan. Now we define the worker agent, which is the core execution component of our system. Unlike the planner, which only creates a strategy, the worker is responsible for actually solving the user's task step by step. So in step 1, we do tracking execution. First, we increment a counter that tracks how many times the worker agent has been called. This is important because it will help us measure iteration cycles and identify whether the system is stuck in repeated revisions or not. In step 2, we are going to inject feedback loop. Next, we construct a feedback signal for the worker. Now, this feedback comes from two sources. One is the reviewer's comment, and then the other is the reasoning evaluator's feedback. And by combining this, we create a closed loop system where the worker can improve its response based on previous mistake. In step 3, we then log the worker's execution step. Now, this helps us trace how many times the worker is invoked during a full run of the system. Then in step 4, we construct the prompt for the language model. We instruct the worker to solve the task step by step internally and return the output in a structured format. Now, the response format is strictly defined in two parts. One is the final answer, and the next is a reasoning trace broken into steps. We also pass in three pieces of context: the original user query, the plan generated by the planner, and the feedback from previous evaluation layers. Now in step 5, we then call the language model with this prompt and capture its response. Since model outputs can sometimes vary in structure, we safely extract the text content from the response. Now in step 6, after receiving the output, we separate it into two parts. If the response contains a reasoning trace section, we split the output into the final answer and then step-by-step reasoning trace. So if the structure is not followed correctly, we treat the entire output as the final answer. Next, in step 7, we store both components into the shared system state. The final answer becomes the draft response and the reasoning trace is stored separately for evaluation. Now, this separation is critical because it allows us to independently evaluate reasoning quality and output quality later on. And in step 8, we save complete worker output into a file. Now, this will help us inspect exactly how the model reasoned and what it produced at each iteration of execution. This worker agent is where planning turns into execution and where we can observe both reasoning quality and behavioral correctness in action. Now we move to the reasoning evaluator agent, which is responsible for analyzing the quality of the model's thinking process. In step 1, logging the evaluation step. So we first log that the reasoning evaluator has started execution. This helps us track when reasoning evaluation happens in a full multi-agent pipeline. In step 2, we define the purpose of this agent. So unlike the worker agent, which focuses on generating answers, this agent does not care about the final output. Instead, it focuses only on how the model arrived at the answer, meaning the reasoning trace. In step 3, which is the evaluation criteria definition, we explicitly define what good reasoning means in the prompt. So basically, the evaluator checks for logical consistency, missing steps in reasoning, incorrect assumptions, hallucinations, and overall coherence of thought. So this makes the evaluation structured rather than subjective. In step 4, where we provide context to the evaluator, so we pass two important inputs into the model. One is the original user query, and then the other is the reasoning trace generated by the worker agent. So this will allow the evaluator to judge whether the reasoning actually aligns with the task requirements. And in step 5, which is the structured evaluation request, we instruct the model to return a strict structured output containing a numerical score from 0 to 10, a choice of approve or revise, and a short reasoning for the evaluation. So this structured format is important because it allows downstream component to easily parse and use the evaluation result. In step 6, we go for model execution, where we invoke the language model and capture its response. We also normalize the output to ensure we can safely process it regardless of formatting differences. In step 7, we identify whether the reasoning is acceptable. So if the output contains the word approve, we mark it as approved, otherwise it is marked for revision. In step 8, we extract the numerical score and reasoning explanation from the output. which will allow us to separate quantitative evaluation from qualitative feedback. And then in step 9, we store three key pieces of information in the system state. One is the reasoning score, the other is approve or revise choice, and the third is the feedback explanation. So this data will later influence whether the system continues iterating or it will stop. And then finally in step 10, we persist the full evaluation output into a file for debugging and analysis. So this layer is what transforms the system from a simple generator into an introspective AI, one that can evaluate its own thinking before producing a final answer. Now we define the output reviewer agent, which acts as the final quality control layer for the system's response. We first increment a counter that tracks how many times the reviewer has been called. So this helps us understand how many revision cycles were needed before reaching a final answer. So unlike the reasoning evaluator, which focuses on internal thinking, this agent evaluates the final output itself. It behaves like a strict human reviewer who judges whether the answer is actually usable. We then define specific criteria for evaluation. First, whether the answer includes examples. Second, whether it has implementation level detail. Third, whether it is clear and easy to understand. And fourth, whether it is actionable. So this ensures we are not just checking correctness but also practical usefulness. Next, we pass two key inputs to the evaluator, which is the original user query and the final answer generated by the worker agent. This allows the reviewer to judge the response in context rather than in isolation. We then instruct the model to return a strict structured output containing a decision, which is approve or revise, and a short reason for that decision. This makes the output easy to parse and integrate into our system logic. We then invoke the language model and capture its response. We normalize the output so that we can safely extract structured information even if formatting varies slightly. We then identify whether the response is acceptable based on whether it contains the word approve. If not, it is marked for revision, triggering another iteration in the system. Then we also extract the reason provided by the reviewer. This feedback will be important because it is fed back into the worker agent, allowing the system to improve in the next iteration result. Next, we store the decision and feedback inside the system state so it can influence the future generations. And finally, we save the full reviewer output into a file for debugging and analysis purpose. So this layer acts as the final gatekeeper, ensuring that even if reasoning is correct, the final output still meets quality, clarity, and usable standards. Next, we define our router function, which controls the flow of the entire system. So it decides whether the current output is good enough to be finalized or needs another iteration. The router checks if both the reasoning evaluator and the reviewer has approved the response. If both are approved, or if the system has already gone through 2 revision cycles, the process stops and the workflow ends. Otherwise, it increases the revision count and sends the execution back to the worker agent for refinement. So this creates a control feedback loop that ensures the system improves its output before producing the final answer. Now we define the core structure of our system using LangGraph, and this is where we convert all individual agents into a single coordinated workflow. So at first, we start by initializing a state-based graph using StateGraph. This means every agent in the system will share a common state object, allowing information to flow between them seamlessly. Next, we register each of our agents as a node in the graph. We add 4 key components: the planner agent, the working agent, the reasoning evaluator, and the reviewer agent. Each of these nodes represent a distinct role in the reasoning and evaluation pipeline. Now we define how data flows between these agents. We set the planner at the entry point, meaning it is the first agent to execute when the system starts. Then we create a fixed sequential flow: planner to worker, worker to reasoning evaluator, and reasoning evaluator to reviewer. So this ensures that every user query passes through planning, execution, reasoning evaluation, and output review in a structured pipeline. After the reviewer agent, we introduce a conditional decision mechanism. This is where the system becomes adaptive instead of strictly linear. We attach a router function that evaluates whether the output is acceptable or needs improvement. If the reviewer and reasoning evaluator both approve the output, the system terminates. Otherwise, the workflow loops back to the worker agent for another iteration. This creates a self-correcting feedback loop, allowing the system to refine its output over multiple cycles. And finally, we compile the graph into an executable application. This step transforms our abstract workflow definition into a fully runnable multi-agent system. And once compiled, we can simply invoke the graph with a user query, and the entire pipeline executes automatically. So this graph is what turns isolated agents into a coordinated reasoning system where planning, execution, and evaluation all work together in a controlled loop. Next, we generate a visual representation of our agent workflow. We convert the LangGraph structure into a mermaid diagram and export it as a PNG image. So this will give us a clear view of how all agents are connected in the system, and if the graph generation fails for any reason, we simply log the error for debugging. And finally, we execute the system. So we take the user query as input and initialize the system state with all required variables for tracking, planning, reasoning, and evaluation. So this state is passed into the LangGraph application, which triggers the entire multi-agent pipeline. And once the execution is complete, we extract the final response from the system state, and we also save the final output into a file for later analysis and print it as the system's final answer. Now let's run the system and then see how the reasoning agent behaves. So Python will run reasoning eval.py. So I have a user query. Let me just paste it here. So my query is design a simple AI-powered customer support system for an e-commerce website. Explain the architecture and suggest how you would evaluate its performance. So let me just run this and then check out what happens. So if we go and browse the log file, then we can see that the worker agent, the reviewer agent has been working on its own. So we'll open one section of this reviewer output, and we'll see that it has been asking to revise because there is lack of implementation details and examples. Let's me do this further. It is asking to revise because it lacks specific examples and implementation details. Again, lack of specific example, implementation detail, and clarity on architecture and evaluation strategy. So it again says the same. I think the worker agent is not able to improve its response yet. Yes, it is doing that further. Let's update this. See, it's still lacking specific example and implementation detail. Let's see what the worker agent is doing here. So we'll open this latest output. So the final answer is the proposed AI customer support system for e-commerce website will utilize that NLP module, something. And then it is giving these reasoning traces here, but the reviewer is not accepting it because it lacks specific examples, implementation detail, and clarity on the architecture and evaluation methodology. So again, this can go up to so many steps. I thought we had prevented it from going on and on, but I think that is not working. But anyway, we can see that that our worker agent is working tirelessly to like redefine its structure in much more detail, and then the reviewer agent is providing its feedback accordingly based on the output of the worker agent. As you can see, previously the worker agent gave a very brief reasoning trace here, but as we went on, the worker agent's trace has been iteratively increasing. So here it's 3 steps, here it's almost 8 steps. In worker output 22, it is much more detailed now, along with addressing the lack of examples and implementation details. Let's go to 23. Again, it has joined everything in the reasoning trace itself. Let's go to 24. So it is kind of improving, and then the reviewer is also giving out its response here. So both of these agents are working in tandem or working alongside each other to providing me the best output that I am looking for. So I'm not going to let this run for infinite cases because there is a cost here for the number of tokens that is being utilized by the model. So I'm going to stop this. But anyway, you can see how this reviewer agent specifically focuses on the process or the reasoning steps of this worker agent, and then provides its answer whether to revise or to approve the answer provided by the worker output here. So now we understand how our multi-agent evaluation system works. So what you just saw here is not just a single pass AI response. Like I said, it's a continuous loop of generation, evaluation, and refinement. So the worker agent generates the solution, the reasoning evaluator checks the quality of the answer, and the reviewer validates the final output. So, and if the reviewer found that something is not good, the system doesn't stop. It goes back and then asks the worker output to improve it again and try again. So this is what makes agentic AI powerful. Not just generating answers, but iteratively improving them through structured feedback. So if you enjoyed this breakdown, in the next video, we'll go even deeper into the behavioral level evaluation and then the system level evaluation and benchmarking of agentic workflows. So I'll see you now in the next video. In the previous videos, we focused on evaluating AI based on its output and reasoning. But there's a critical layer that most people ignore, and that is behavior. In this video, we are going to evaluate how an AI agent actually behaves while solving a task. Not just what answer it gives, and not just how it thinks, but what actions it takes. We'll build a system where the AI has access to multiple tools like search, code execution, and database queries. And instead of trusting the agent blindly, we'll track every action it takes step by step. Then we introduce a behavior evaluator that checks whether the correct tool was used, whether any unnecessary steps were taken, and whether the sequence of action makes sense. So now our system doesn't just evaluate output and reasoning, it evaluates the decision-making process of the agent itself. And by the end of this video, you'll have a complete multi-agent system that can track actions, evaluate behavior, and improve itself through feedback loops. So let's start by setting up the basic structure of this system. We start by importing the required libraries for building our multi-agent system. We use standard modules like OS and logging for file handling and tracking execution. Then we load environment variables using .env, which allows us to securely manage API keys. We also import LangGraph, which we'll use to define and connect our agent into a workflow. And finally, we initialize our language model using ChatGroq with the Llama 3.3 70 billion model, which will power all reasoning in our system. Next, we set up logging and file tracking for the system. So this will allow us to record everything that happened during execution, including agent output and intermediate steps. We also create a utility function to save these outputs into separate files, so we can easily inspect the agent's behavior and debug the system whenever needed. Next, we define a set of tools that our agent can use while solving tasks. These are simulated tools, but they represent real-world capabilities of agentic systems. The first one is the search tool, which simulates retrieving factual information from web or external sources. The second is the code tool, which represents executing computations or running code, for example, solving calculations or transforming data. And finally, we have the database tool, which simulates querying structured data from our database. So instead of relying only on the language model, the agent can now take actions and interact with different type of information sources, just like real-world AI systems. Next, we define the planner agent. Just like before, the agent is responsible for understanding the user query and creating a short actionable plan. It doesn't execute anything, it simply decides what needs to be done. We pass the user query to the language model and ask it to generate a structured plan. This plan is then stored in the shared state so that the worker agent can follow it during execution. We also save the planner output to a file so we can inspect how the system is approaching the problem. This step is important because it sets the direction and later will evaluate whether the agent actually follows this plan correctly through its actions. Now we come to the worker agent, and this is where behavior actually happens. So unlike the planner, this agent doesn't just decide what to do, it actually executes the task. But more importantly, in this setup, it doesn't just produce an answer, it performs actions. First, we collect feedback from previous iterations, including behavior feedback, reasoning feedback, and the reviewer comments. This allows the worker to improve its action over time, not just its final answer. We also initialize something called an action trace. This will record every step the agent takes, which tool it used, what input it gave, and what result it got. Now, we define a structured prompt that turns the model into a tool using agent. We explicitly tell it what tools are available, when to use each tool, and strict rules to follow. For example, it must choose the correct tool, it should not hallucinate if a tool is required, and it only can use one tool per step. These rules are critical because later we'll evaluate whether the agent actually follows them or not. We also enforce a structured format, thought, action, and action input. This allows us to clearly extract and track each decision the agent makes. We then pass the user query, plan, and feedback into the model and generate the full response. Now comes the key part. We parse the model output line by line. Whenever we detect an action and its input, we simulate the corresponding tool. Based on the action, we call the search tool or the code tool or the database tool, and we capture the result of that action. Each step is stored in the action trace as the tool used, the input, and the result. So this will give us a complete record of the agent's behavior. We also extract the final answer and the reasoning trace. And all of this is stored in the system state: the answer, the reasoning, and the full action trace. And finally, we save both the raw output and the action trace into files so we can inspect exactly how the agent behaved. This is the core of behavior evaluation. We're not just looking at the answer, we're tracking every decision the agent makes while solving the problem. Now we define the behavior evaluator, and this is where things get really interesting. Up until now, we've tracked what the agent did using the action trace, but here we actually judge whether those actions were correct. This agent is not looking at the final answer, it is evaluating the decision making process of the agent. We define very specific criteria for good behavior. Did the agent choose the correct tool? Did it misusing a tool when it was required? Did it take unnecessary steps? Was the execution efficient? And did the actions follow a logical order? We also explicitly tell the evaluator what each tool is meant for: search for factual information, code for computation, and database for structured queries. This allows the evaluator to detect misuse of tools. And we pass two key things into this agent. One is the original query or the original user query, and the action and the full action trace generated by the worker. So the evaluator has complete visibility into what the agent actually did. We also enforce strict rules like using a wrong tool is a major penalty, not using a tool when needed is also penalized, and unnecessary actions reduce the score. Then we ask the model to return a structured response, a score from 0 to 10, a choice, whether to approve or revise, and a short explanation. We then extract the choice and feedback from the model's response. If the behavior is not good enough, it will be marked for revision. This feedback is stored in the system state and sent back to the worker agent in the next iteration. So now the agent does not just improve its answer, it improves how it behaves. And finally, we save the full behavior evaluation into a file so we can inspect and debug it. And this is what truly makes the system agentic. We are not just evaluating results, we are evaluating actions. Next, we define the reasoning evaluator. This agent evaluates the thinking process of the model. We pass in the user query and the reasoning trace generated by the worker and ask the model to judge how good that reasoning is. And just like the behavior evaluator, it returns a score, a choice whether to approve or revise, and a short explanation. Now, this might look very similar to the behavior evaluator, but they are actually evaluating completely different things. Behavior evaluation looks at what action the agent took, which tools it used, and whether those actions were correct or not. It basically focused on external actions. Whereas reasoning evaluation, on the other hand, looks at how the agent thinks, whether the logic is correct, and whether the steps make sense. So it focuses on internal thinking. Behavior is what the agent does, and reasoning is how the agent thinks. Just like before, the feedback from this evaluator is stored in the system state and passed back to the worker agent. So now, the agent improves not just its actions, but also its thinking. And finally, we save the reasoning evaluation output into a file for inspection. And together, behavior and reasoning evaluation gives us a complete view, both the decisions the agent makes and the logic behind them. Next, we define the output reviewer. This agent evaluates the final answer generated by the system. We pass in the user query and the final response and ask the model to judge whether the answer is good enough. And similar to other evaluators, it returns a choice whether to approve or revise and a short reason explaining that choice. And at this point, we've already evaluated how the agent behaved and how it reasoned, but this layer focuses purely on the final output. So behavior checks actions, reasoning checks thinking, and reviewer checks the final answer. And if the answer is not good enough, the feedback is passed back to the worker agent for another iteration. We also store the reviewer output in a file so we can track how the system is improving over time. And this finally acts as a final quality gate before the system decides whether to accept or refine the response. Next, we define the router, which controls the decision flow of the entire system. This function checks whether all three evaluation layers have approved the result or not. One is behavior, the other is reasoning, and the other is final output. If all three are approved, the system stops and returns the final answer. We also add a safety condition, so if the system has already gone through two revision cycles, we stop to avoid infinite loops. And if any of the evaluation fails, our system increases the revision count and sends the workflow back to the worker agent. So the system doesn't just improve randomly, it improves until all three agents agree the solution is good enough. And this is what turns the pipeline into a self-correcting actions. Now we define the graph, which is the backbone of our entire system. And this is where we connect all our agents into a single structured workflow. Instead of running agents independently, we define a controlled execution pipeline. We first register all agents as a node in the graph, planner, worker, behavior evaluator, reasoning evaluator, and reviewer. Each node represents a specific role in the system. We then define a strict execution order. The flow starts with the planner, then moves to the worker, followed by behavior evaluation, reasoning evaluation, and finally output review. At the reviewer stage, we don't follow a fixed path. Instead, we attach a conditional router that decides whether the system should go or stop for improvement. If any evaluation fails, the system loops back to the worker agent and tries again. This creates a controlled iterative refinement loop. And finally, we compile the graph into an executable application. At this point, our multi-agent system becomes fully runnable as a single pipeline. So instead of isolated agents, we now have a fully connected evaluation-driven AI system. And finally, we define the code for running the system. We start by taking a user query as input from the user. We then initialize the system state with all the required variables. This includes tracking the user query, storing the plan, reasoning trace, and action trace, and maintaining evaluation results from all three layers: behavior, reasoning, and output. We also initialize counters to track how many times each agents run during execution. This state is then passed into our compiled LangGraph workflow. From here, the entire multi-agent system takes over, running the planner, worker, evaluators, and reviewer in a control loop. Once execution is complete, we extract the final response from the system state. This is the final approved answer after all evaluation layers have agreed. And finally, we get the final output to the user. So what we get is not just a model response, but a fully evaluated, multi-layer verified AI output generated through an iterative agentic system. Now let's run the system. So I'll run Python behavior eval.py. And then let's run this system with a real query. So let's say my query is calculate 25 times 16 and then explain step by step how you arrived at the answer. So let me clear all of these logs that I have from previous run. Okay, let's clear this. Let's first delete these logs. And then run this again. Now again, the query is going to be the same. So here we have passed a complex problem that requires not just reasoning, but also choice making about tools usage, right? So the agent now needs to understand the problem, create a plan, choose which tools to use, execute action step by step, and finally get evaluated on behavior, reasoning, and output quality. So as the system runs, each agent takes over sequentially, starting from planning, then moving to execution and refinement loops. And what makes it interesting is that the response you see at the end, or I'm not getting any response here. So let's see what the final worker output was. Okay, so the response you see at the end here is the result of multiple evaluation cycles, as you can see. So the final answer is only produced when all three layers agree that the behavior is correct, the reasoning is solid, and the output is high quality. So this is not just a single LLM call. As you can see from the logs here, this is a full system or a full AI system that thinks, acts, evaluates, and improves before you get the final answer. So let's review what it did here. Let's start with the worker output first. Let me close this. We already have the answer, so this is not needed. So at first, it says that to calculate 25 times 16, we need to perform multiplication operation. So the action is code tool, and the action output is 25 times 16. So the thought is that the code tool will provide the result of multiplication, which we then can use to explain step-by-step process. And then the action needed is none, as the calculation is straightforward, and the final answer is 400. So in the reasoning trace, it said that we identify the problem as a multiplication operation between 25 and 16. And in step 2, we chose to use the standard multiplication method, but in this case, we use the code tool to directly calculate the result, which is equivalent to multiplying 25 times 10 and 25 by 6, which 10, and then adding the results together. So based on this particular worker output, then we go to our reviewer output. Okay, first of all, we'll see what the reasoning evaluation told us. I think we've only stored one reasoning evaluation. Let's go to action trace. So in action trace, the first one actually, so it said to use the code tool here. And for the review part, what it says is the answer lacks step-by-step explanation as requested in the query, and it asks to revise. Now, when we go to the final worker output, now it has the complete reasoning trace as well as the answer here. What was the review? Let's see the review. So to calculate 25 times 16, we follow the steps, multiply the number, perform the multiplication, and add the results together. So here the model or the reviewer agent approved the decision, and then the answer was provided here. So based on this, let's see what the reasoning eval told. So this was also approved by the reasoning evaluator. The reviewer agent also approved it, and then the behavior agent also approved the final answer. And as a result, we got that final answer. I think that is an execution log. Let's see. So even though the answer was not printed out, but still we got our final answer here. So this is what behavior evaluation of agentic AI systems are. So in the next video, we are going to see the system evaluation. So far, we've evaluated AI systems at 3 levels: output, reasoning, and behavior. But there's one problem. Even if all 3 are perfect, the system itself can be inefficient. What if the agent takes too many steps? What if it calls tools unnecessarily? Or what if it keeps looping again and again? That is where system level evaluation comes in. In this video, we are going one level higher. We are not just evaluating what the AI says or how it thinks. We are evaluating the entire system performance. We'll track things like execution time, number of iterations, tools usage, and overall efficiency. And based on all of this, we'll generate a system score, a single number that tells us how good our entire AI pipeline really is. Because in real-world AI system, correctness is not enough. Efficiency is everything. So let's build a system that doesn't just think and act, but also know how well it's performing. We'll start with the basic setup. We import essential libraries like OS and logging for file handling and tracking execution, and time to measure how long our system takes to run. Next, we load environment variables using .env and bring in LangGraph to build our multi-agent workflow. And for the language model, we'll use the Groq LLM through LangChain, specifically the Llama 3.370 billion versatile model. This model will act as a brain behind all our agents from planning to execution. Next, we set up logging for the entire system. We create a logs directory where all output, evaluation, and intermediate steps will be stored. Then, we configure a logging system to track everything that happens during execution, including timestamps, log levels, and messages. We also define a helper function to write outputs into text files. This will be important because system evaluation is not just about the final result. We need visibility into every step the system takes. Next, we define the tools that our agent can use. They are simple simulated tools, but they represent real-world capabilities in an AI system. Here are three tools we define. The search tool is used for retrieving factual information. The code tool simulates executing computations or running logic. And the database tool represents querying structured data. So now, instead of generating text, our agent can actually take actions and interact with different types of data sources. Next, we define the planner agent. This agent takes the user query and generates a short plan for how the problem should be solved. It doesn't execute anything, it simply decides the steps the system should follow. We pass the query to the model, store the generated plan in the shared data, and also save it to a file for inspection. And this plan will act as a blueprint that guides the entire system during execution. Now we move to the worker agent, and this is where the actual execution happens. The agent is responsible for solving the task using tools. But unlike a simple LLM call, this agent doesn't just generate an answer. It takes action step by step. We start by incrementing the worker call count, and this helps us later measure how many times the system had to retry, which is a key part of system evaluation. Next, we collect feedback from previous iterations. Behavior feedback, reasoning feedback, and reviewer feedback. And this will allow the agent to improve not just its answer, but also its choices over time. Then we initialize an action trace. This will store every action the agent takes. You can think of this as a log of agent's behavior. And now we design a structured prompt that turns the model into a tool agent. We clearly define what tools are available, what each tool is used for, and strict rules to follow. For example, here you can see that the agent must choose the correct tool and it can only use one tool per step. These kind of rules or constraints are critical for evaluating behavior later. Then we enforce a format: thought, action, and action input. This structured format makes it easy to extract and simulate each step programmatically. Next, we pass the query, plan, and feedback into the model and generate the full response. And now comes the key part. We parse the model's response line by line. Whenever we see an action, we store it. Whenever we see an action input, we execute the corresponding tool. So depending on the action, we either call the search tool or the code tool or the database tool. And this simulates real-world tool usage. Each action here is recorded with tool used, input, and the result. This gives us a complete record of how the agent behaved. Then we also extract the final answer from the output. We store the final answer and the action trace in the system state. And finally, we save the full worker output to a file so we can inspect the execution. Now, this step is crucial for system evaluation because metrics like tool usage, number of steps, and retries all come from this execution process. Next, we define the behavior evaluator, and this is one of the most important components of the system. Up until now, the worker agent has been taking actions, selecting tools, executing steps, and building an action trace. But here, we step in and ask a critical question. Did the agent behave correctly while solving the problem? This evaluator does not care about the final answer. Instead, it focuses entirely on how the answer was produced. We pass two key inputs, the original query and the complete action trace generated by the worker agent. This gives the evaluator full visibility into every step the agent took. We explicitly instruct the model to evaluate behavior based on correct tool usage, efficiency of execution, and overall correctness of actions. For example, did the agent use a code tool when computation was required? Did it unnecessarily call a search tool? Did it take extra steps that could have been avoided? These are all signals of good or bad behavior. We ask the model to return a structured result, a score between 0 and 10, a choice between approve or revise, and a short explanation. From the model's response, we extract whether the behavior is approved or needs revision. If the behavior is not good enough, the feedback is stored in the system state. This feedback is then passed back to the worker agent in the next iteration. So now, the agent doesn't just improve its answer, it improves how it acts. We also save the full evaluation output into a file. This allows us to debug and understand exactly where the agent went wrong. And this is what separates basic LLM systems from true agentic systems. We are not just evaluating results, we are evaluating its choices. Because in real world AI systems, How you get the answer is just as important as the answer itself. Next, we evaluate the reasoning of the system. While behavior evaluation focuses on action, this agent focuses on thinking. It checks whether the logic behind the solution is correct and meaningful. Even if an agent uses the right tool, it can still reason incorrectly. So here, we evaluate whether the system is actually thinking properly or not. We pass the original query to the model. In a more advanced setup, we could pass a detailed reasoning trace, but here we keep it simple and focus on overall reasoning quality. The model judges whether the reasoning is logically sound, whether the steps make sense, and whether the solution approach is valid. And just like before, it returns a score from 0 to 10, a choice between approve or revise, and a short explanation. We then extract whether the reasoning is approved or needs revision. If the reasoning is weak, this feedback is passed back to the worker agent. So now the system improves not just its action, but also its thinking process. And we also save the reasoning evaluation output into a file for analysis. So at this point, behavior checks what the agent does, reasoning checks how the agent thinks. And together, these layers ensure the system is both correct in action and sound in logic. Next, we define the reviewer, the final evaluation layer. At this stage, we evaluate the final answer itself. So after checking behavior and reasoning, we now ask a simple question. Is the output actually good enough for the user or not? This agent focuses purely on output quality. It doesn't care how the answer was generated. It only cares whether the final result is correct, clear, and useful or not. We pass the final response generated by the worker agent. The model then evaluates the answer and returns a choice between approve or revise and a short explanation. We then extract the choice from the model's response. If the answer is not good enough, it will be marked for revision. This feedback will be stored and passed back to the worker agent. So now the system improves the final output quality as well. And we also increment the reviewer call count. This will help us track how many times the system had to review the answer, which is important for system level evaluation. And finally, we save review result into a file. This gives us a history of how the output improved over multiple iterations. So now we have behavior evaluation, judging actions, reasoning evaluation, judging thinking, and reviewer judging the final answer quality. And this acts as the final quality gate between the system or before the system decides whether to accept or refine the response. Next, we define the router. This function will act as the control center of the entire evaluation loop. It chooses whether the system has reached a good enough solution or needs another iteration. We check three evaluation signals here: reviewer decision, reasoning decision, and behavior decision. If all the three evaluators approve the output, then the system is considered successful. At that point, we terminate the workflow and return the final result. If any one of the evaluation fails, we increase the revision count. Then we send the system back to the worker agent for another attempt. So this router is what turns the system into a feedback-driven loop. It continuously pushes the agent to improve until all three evaluation layer agrees. And this is what makes the system self-correcting. It doesn't stop until it meets all quality standards. Next, for the purpose of this video, we compute a system level score for the entire agent. This function will give a single score out of 10 based on how efficiently the system performed. We start with a score of 10. Then we reduce the score based on different conditions. If the system takes more than 10 seconds, we subtract 2 points. If the system needed more than 2 revisions, we subtract 2 points. If too many tools were used, more than 6, we subtract 2 points. And if the worker agent ran more than 3 times, we subtract 2 points. And finally, we return the score, making sure it does not go below 0. So this will give us a simple score that tells how efficient the whole system was, not just whether it worked, but how cleanly it worked too. Now we define the graph, and this is where we connect all the agents together into a single workflow. We're building a state graph using LangGraph where each node represents one agent in the system. First, we register all the components: planner, worker, behavior evaluator, reasoning evaluator, and reviewer. Each of these nodes represents a different stage in the AI pipeline. We set the entry point to the planner, so every user query first goes through planning before anything else happens. Then we define a fixed execution flow: planner, worker, behavior evaluation, reasoning evaluation, and reviewer. After the reviewer step, we don't stop immediately. Instead, we pass the result into a conditional router. If the output is not good enough, the system goes back to the worker. If all evaluations are approved, then the system ends. And finally, we compile the graph into a executable application. So this graph defines the full life cycle of the agent, from planning to execution to multi-layer evaluation and feedback-driven iterations. And finally, we come to the execution part where this entire system actually runs. First, we take the user query as input, and this is going to be the starting point of the entire agentic workflow. Then, we define the initial state dictionary. This acts like a shared memory for the entire system. It stores everything the agent will generate during execution, such as the plan, the final response, action traces, evaluation feedbacks from all layers, and counters for tracking iterations. And before running the system, we'll start a timer. This will be important because we want to measure how long the entire pipeline takes to execute. Next, we invoke the LangGraph workflow. At this point, the full multi-agent system runs, including planning, tool execution, and all the evaluation layers. And once the execution is complete, we stop the timer. Then we calculate the total execution time. And next, we compute the system level metrics. We extract the total execution time, number of worker calls, number of reviewer calls, number of revisions, and the total tool usage. These metrics are then passed into a scoring function that we built earlier. This function will calculate a final system based on or a final system score based on efficiency and performance. Then we combine all the metrics and system score into a single report, which will give us a complete summary of how the system performed. We'll save this report or we'll save the system evaluation report into a file which can be used to analyze performance later or compare across runs. And finally, we'll print out the final response generated by the agent and then the full evaluation report here. So here in this section, everything comes together. We don't just get an answer, we also measure how efficiently it was produced, how many iterations were needed, and how well the system performed overall. And this completes the full agentic evaluation pipeline from execution to measurable system intelligence. Now let's run the code and evaluate the response or look at the final system evaluation report. So for this, I'm going to do python system eval.py. The program is going to ask me for a query, and I'm thinking of providing a mathematical question in the query section. So let me pass this particular question here. So if a product cost 1,000 and gets a 10% discount, compute final price without with reasoning. So let's enter this and then let the system run, and we'll finally evaluate what the system did. So this was completed within just one single evaluation system, or one single iteration. So let's go to the planner. So the short plan here generated by the LLM is computing final price with discount. At first, it planned to identify the original price, which costs 1,000. Then it planned to calculate the discount amount, which is 100. It then subtracted the discount from original price, which is 900, and then it went on to identify the final price. The reasoning was the discount reduces the original price by a percentage of original scale. So yeah, this was the plan. Now based on this, let's go to the worker agent, what it did. So based on the plan, the worker agent said that it needed to first identify the original price, calculate the discount amount, subtract this amount from original price, and finally determine the final price. So here the action was code tool. The original price was 1,000, discount percentage was 10, and yeah, the thought was that the code tool will perform the calculation based on the given inputs and formula, providing the final price after applying the cost. So no additional action needed, as the completion directly leads to the final answer, and it was the final answer. Let's see the behavioral evaluation here. So the behavioral evaluation, it evaluated based on correctness. So the final price is correctly calculated. Efficiency, the tool usage is efficient. It also evaluated based on the appropriateness of tool used. Okay, and then it gave a score of 9 out of 10 because it says that the score is high because the tool was used correctly and efficiently to solve the problem. The only reason it's not a perfect score is that for very simple calculation like this, a non-code based mathematical approach might be considered. Okay, the explanation is also quite good. The decision is to approve, and then the reason is accurate and efficient calculation. Let's go to the reasoning evaluation now. And the reason it gave was that the calculation correctly applies the discount to the original price, providing the clear and logical step-by-step reasoning process to arrive at the final price. Okay, so this is also good. Now let's go to the system evaluation, and then we can see the system evaluation here too. So it says the worker call is just 1, reviewer call is 1, revision count is 0, yes, and the tool calls is 1, and the system score is 10. Let's try it with a much more complicated query than this one and see what happens. So we'll run this again, but first of all, I'm going to clear these logs. And then pass in something interesting that everyone, basically all of the content creators would like to know. So explain how a recommendation system works in platform like YouTube, including how user data is collected, how content is ranked, and how feedback improves future recommendations. So this might go to like many number of evaluations, but let's see what happens. We will let the system run until the token finally runs out here. So we'll just start this and see what happens. Okay, so this actually did not take much long, and you can see that it went on for approval in just 1 reviewer call and 0 revision count. So planner worked just as we wanted. The worker the worker agent also did its work. The behavioral evaluation gave a score of 8. It was not 10, but it gave a score of 8 and chose to approve. The reasoning evaluation also gave a score of 8 and then chose to approve. And finally, in the system evaluation, we can see at the end here too the part of system evaluation is complete, and here we have our final output answer. So that brings us to the end of this system evaluation setup. So in this video, we did not just build an AI agent, we built a complete evaluation pipeline around it. And the system does not just generate answers, it monitors itself while generating them. We introduce behavior evaluation to check tool usage, reasoning evaluation to check logical thinking, and output evaluation to ensure final answer quality. All of these evaluations are connected through a feedback loop, like I said. So if the system makes a mistake, it doesn't just stop there, it goes back and improves and tries again. And on top of that, we also added some system metrics to measure efficiency, speed, and overall performance. So we are not just judging correctness, we are also measuring how well the system behaves as an AI system. And this is a shift from simple LLM output to real agentic evaluation systems, where every response is not only generated but also analyzed, scored, and improved. And this is just the beginning, because once you can evaluate AI systems like this, you can start building systems that improve themselves automatically. So if you made it till here, you now understand how a full agentic evaluation system actually works under the hood. If you found this helpful, make sure to like the video. It really helps the channel grow, and subscribe if you want to see more deep dives into AI systems like agentic workflows, LLM evaluation, and real-world AI engineering. In the upcoming videos, we'll go even deeper and build more advanced agent structures. So thanks for watching, and I'll see you in the next one.